In this session, we'll be learning about Euler's Totient function. So what is this function? It is also known as the phi function, and it is represented as phi of n. So what this function returns is it returns the count of numbers ranging between 1 and n, and all these numbers are co-prime to n. So let me repeat that again. So this function, what it gives me is just a count. And what that count is, it is nothing but the count of all the numbers ranging between 1 less than equal to x less than n. So numbers between 1 and n, and all these numbers are co-prime with n. What do you mean by co-prime with n? Based on our previous lectures, we have understood co-prime numbers are numbers wherein the greatest common divisor is 1. So again, let me repeat what is Euler's torsion function. It is a function that gives us the count of the number of numbers ranging between 1 and n that is having a GCD of 1 with n. We'll understand this function with a simple example. Let's say if I take pi of 6, what we'll do is we'll first write all the numbers between 1 and 6. So 1, 2, 3, 4, 5, 6. The next step is we have to find all the numbers in this set which is having a GCD of 1 with 6. Or else what are the numbers here that are co-prime with 6? So 1 and 6 GCD is 1. 2 and 6 GCD is not 1. So we leave this. 3 and 6 GCD is not 1. 4 and 6 GCD is not 1. 5 and 6, yes, GCD is 1. And 6 and 6 GCD is not 1. So the total numbers or co-prime numbers from this set that have a GCD as 1 with 6, it is 2 numbers. So what is this pi of 6? It is nothing but the count of numbers. How many numbers we have? 2 here. So Euler's torsion function is all about the count of numbers that have a GCD as 1 within the range 1 to 6. Let's take another example. Let's find pi of 9. So it just means get the count of all the numbers between 1 and 9 that has a GCD of 1 with 9. Let's write all the numbers between 1 and 9. 1, 2, 3, 4, 5, 6, 7, 8, and 9. So we have to identify all the numbers between 1 and 9 that has a GCD of 1 with 9. 1 is co-prime with every other number, so 1 is accepted. 2 has a GCD of 1 with 9. 3, no. 4 has a GCD of 1 with 9. And 5 has a GCD of 1 with 9. 6, no. 7 has a GCD of 1 with 9. And 8 has a GCD of 1 with 9. So what are the numbers we have identified here? It is 1, 2, 4, 5, 7, 8. So we have 6 numbers that have been identified and they have a GCD of 1 with 9. So pi of 9, Euler's torsion function of 9 should give us the result 6. I hope you would have understood what Euler's torsion function and what result it returns with these examples. Let's go further and look at the properties of Euler's torsion function. We have three main properties. We'll understand each of the property with some sample values. Let's take a look at the first property. What this property says is if p is a prime number, then GCD of p comma q is equal to 1 for all numbers ranging from 1 less than p. So all the numbers q ranging from 1 less than p will be co-prime with p. Therefore, we can state that pi of p is equal to p minus 1. Let's understand this with a simple example. Let's take pi of 5. 5 is a prime number. So we'll first write the set like all the numbers between 1 and 5. 1, 2, 3, 4, 5. So how many numbers here have a GCD of 1 with 5? It is 1, 2, 3, 4. GCD of 5 and 5 is 5, so this is not acceptable. So how many numbers we have here is 1, 2, 3, 4. So pi of 5 is actually gives us a count of 4. So we can generalize this. For instance, if you take another prime number, say pi of 13, we can very well say the output will be nothing but 13 minus 1, that is 12. And why we say this is because all the numbers ranging from 1 less than 13, they will be co-prime with 13, right? So that's why we say pi of 13 is equal to p minus 1. If you really wanted to understand this for better, what you have to do is you have to write all the numbers, say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So what this property says is all the numbers starting from 1 less than 13, they are going to be co-prime with 13. You can very well check that 1 is co-prime with 13, 2 is co-prime with 13, 3 is co-prime, 4, 5, 6, everything is co-prime with 13. That is 7 and 13 as a GCD of 1, so we say it's co-prime. So you take any prime number, all the numbers starting from 1 less than that prime number will be co-prime with that number. So whenever you have a prime number, we can very well say the number of numbers that will have a GCD 1 with a prime number is prime number minus 1. So that is 16. When I say pi of 17, the count of numbers having a GCD of 1 with 17 is 16. So that is the first property. Okay, now let's take a look at the second property of Euler's torsion function. What this property says is if p is a prime number and k is greater than or equal to 1, then there are exactly p power k by p numbers between 1 and pk that are divisible by p, which gives us pi of p raised to the power k is equal to p power k minus p power k minus 1. Let's understand this property with an example. Let's consider this example. P is a prime number, so we'll take 2. We'll raise it to the power 3, wherein k should be greater than or equal to 1. So 3 is greater than or equal to 1. It satisfies that. So what they say is the count of this is nothing but this is equal to 2 power 3 minus 2 power 3 minus 1. So this is nothing but 2 power 3 is 8 minus 2 power 3 minus 1 is 2 square, that is equal to 8 minus 4. So we get the result 4. If you want to verify this, you can very well verify this. What is pi of 2 power 3? That is nothing but 8. So what is pi of 8? For that we have to write the entire set. So 1, 2, 3, 4, 5, 6, 7 and 8. So in this set, how many numbers have a GCD of 1 with 8? So you have 1, you have 3, we have 5 and we have 7. So how many numbers we have here? 1, 3, 7 and 8. So the result is actually 4. This matches this result. So what this property says, whenever you have a prime number raised to the power k which is greater than or equal to 1, then we can compute the count by doing this. The prime number power k minus prime number power k minus 1. I hope you have understood this property. Let's go to the third property. The third property says if a and b are relatively prime, then pi of ab is equal to pi of a into pi of b. Please keep this in mind, a and b are two different numbers. Let's understand this with a very simple example. Say for instance, if you have pi of 15, pi of 15 can be represented as the multiplication of pi of 3 into pi of 5. We just represent the number as a multiplication of two prime numbers. So once when you know this, you can very well go and substitute the first property. When what is pi of a prime number? It is p minus 1. So pi of 3 is 2. According to the first property of Euler's torsion function, pi of a prime number is nothing but pi of p minus 1. that is 4. So we get 8. When you are representing a number in the multiples of a prime number, please keep in mind that all the numbers should be distinct numbers. You should never perform this. For instance, if you have 49, you cannot represent 49 as pi of 7 into pi of 7, because these two are not distinct numbers, whereas pi of 49 can be represented as pi of 7 the whole square. So when you have a prime number raised to the power k, how you find the result? It is nothing but 7 square minus 7 power 2 minus 1, that is 7 square minus 7, or you can say it is 49 minus 7, that is 42. So you should not solve this kind of an problem like this, because this is not pi of a into pi of b. A and b should be distinct numbers, so this is not allowed. We have to solve this like this. Can we take another example? Can you solve this? Pi of 6. Pi of 6, it's actually not a prime number. So what we can do is we can represent that as a multiples of prime number. For instance, pi of 2 into pi of 3. And what is pi of 2? It's 2 minus 1. And what is pi of 3? 3 minus 1, that is 2. So we give 2. So this is based on the first property. Pi of p, when p is a prime number, that is equal to p minus 1. So this is what we have achieved. And we can very well verify that if you take all the numbers from 1 to 6, 3, 4, 5, 6, how many numbers actually has a GCD of 1 with 6? It's just 1 and 5. So only these two numbers have a GCD of 1 with 6. So 1 and 5 are co-prime with 6. So the number of numbers having a GCD of 1 is 2. So that is verified. So we have understood the properties of Euler's torsion function. We'll now take up some exercises. Can you give me the results for all these things? Pi of 20, is 20 a prime number? No. So what we can do is we can represent 20 like this. This is pi of 5 into pi of 2 square. So what is pi of 5? So it's a prime number. So it is nothing but 5 minus 1 into, what is pi of a prime number raised to the power k? It is 2 square minus 2 power 2 minus 1. So this is 4 into, it's actually 4 minus 2. So this is 4 into 2, 8. So pi of 20, the result is 8. I hope you all have received that result. Now can we solve what is pi of 21? What is pi of 21? See, 21 is not a prime number. So we can represent 21 as multiples of a prime number. For instance, we can say it's pi of 3 into pi of 7. So we'll apply property 1. What is pi of p when p is a prime number? It is p minus 1. So 3 minus 1 into, and this is 7 minus 1. So it is 2 into 6. So 12. So this is the result for the second problem. Let's take the third problem. Pi of 19. Is 19 a prime number? Yes. So you can very well say the answer is 19 minus 1, that is 18. Let's take pi of 45. Can you find the result for pi of 45? So what is pi of 45? Pi of 45 can be written as multiples of pi of 5 into pi of 3 square. So 9, I'm just writing it as 3 square. So now applying the first property here, 5 is a prime number. So it is 5 minus 1 into, and now applying the property number 2, we'll solve this as 3 square minus 3 power 2 minus 1. So this is nothing but 4 into, this is 9 minus 3. So this is 4 into 6, that is equal to 24. So the result for pi of 45 is 24. So you should never forget what is an Euler's Totient function. If you take a function pi of n, what we are going to determine is nothing but the count of all the numbers in the range 1 to n, which is actually co-prime to n. That's about Euler's Totient function. Now let's take a look at the Euler's theorem. What this theorem states is, if a and m are two positive integers that are co-prime, then we can very well say a per pi m is congruent to 1 mod m, where pi of m is the Euler's Totient function which we have just now seen. We'll understand this with an example. The very important criteria here is GCD of A and M should be equal to 1. Only then we can say this holds. Let's understand this with a simple example. Let's consider A to be 3 and M to be 10. So the first thing we have to check is whether GCD of 3 comma 10 is equal to 1. Yes, GCD of 3 comma 10 is equal to 1. So 3 and 10 are relatively prime, or we can call them to be co-prime numbers. So our condition is satisfied. Now we can substitute these values in this equation. That is 3 raised to the power 5 of 10 is congruent to 1 mod 10. We have to compute pi of 10, which is the Euler's torsion function. For that, we can use this property, pi of AB is equal to pi of A into pi of B. So we can use this property. So we'll split pi of 10 like, we'll use the prime factors for 10. So we'll split it as pi of 2 into pi of 5. So this is the property we have learned that with Euler's torsion function. So what is pi of 2? Pi of a prime number is nothing but prime number minus 1. So this is nothing but 2 minus 1 star. Again pi of 5 is 5 minus 1. So this is nothing but 1 into 4. So that is 4. So pi of 10, the value of pi of 10 is 4. We can substitute that here. 3 per 4 is congruent to 1 mod 10. Let me go to a white screen and continue. So what we have achieved is 3 per 4 is congruent to 1 mod 10. So this is what we have achieved in the previous slide. And we can very well prove this. What is 3 per 4 is congruent to 1 mod 10 means it is nothing but 3 per 4 mod 10 is equal to 1 mod 10. This is the meaning of congruence, right? So what is 3 power 4? It is 81 mod 10 is equivalent to 1 mod 10. So 81 mod 10 is 1, 1 mod 10 is 1. So we clearly understand that when we have A and M to be two co-prime numbers, we can very well say A per pi M is congruent to 1 mod M. So this holds. And this is what the Euler's theorem states. Okay, we have understood the Euler's theorem. Now let's take an exercise. Can you compute and tell me the value for this? 2 and 4 raised to the power 5 and 2 mod 5 and 3. Can you tell me the value? The very first step we have to check is what is the GCD of 214 and 513. So we'll compute the GCD of 214 and 513. If you compute that, you will know that the GCD is 1. So we say 214 and 513 are co-prime numbers. So once when they are co-prime, we can very well use it in our Euler's theorem, that is 214 raised to the power pi of 513 is congruent to 1 mod 513. So what is pi of 513? 513 is a prime number, and when you do apply the Euler's Totient function on 513, it is nothing but 513 minus 1, that is equal to 512. So what we arrive at here is 214 raised to the power 512 is congruent to 1 mod 513, and we can very well say that 214 for 512 mod 513 will be equal to 1 by applying the Euler's theorem, because we see 214 and 513 have a GCD of 1, and so this equation actually satisfies the form a power pi m is equal to 1 mod m. So we can very well conclude 214 for 512 mod 513 is equal to 1.